we are going to do something more interesting. It is two-dimensional motion. Okay, what is it all about? Yeah, something like this, right? If you are going to throw a shot put, let's say for example, you throw a shot put, you are going to throw it at an angle with the horizontal. So the angle with the horizontal is theta degrees, theta degrees. And at the starting point there, the velocity is v naught. So I enlarge this starting point here on this side, on this side. Okay, right. So the starting velocity or the initial velocity is the red line. Okay, is the red line. So this velocity, we call it v naught. And this velocity can be resolved into two components. Resolve, I better, because maybe the sound system not so good and my pronunciation not so good. Resolve. Okay, so this is the word, resolve. So the velocity at an angle like this can be resolved into two components. So the horizontal component, which is this one, the horizontal component, is called v naught x. So the x there indicate that it is the horizontal component. And the vertical component here is v naught y. So v naught is the initial velocity and y represents the vertical component of it. V naught represents the initial velocity and v naught x is the horizontal component. Okay, let's say don't know what I'm talking about. So we look at one example, one numerical example. Let's say if I were to throw an object at an angle like this, this is at an angle with the horizontal, and the velocity as the ball or the shot put leaves my hand is 10 meter per second. As the object leaves my hand, it is 10 meter per second. Now, when the object travel in this direction, it has actually two components. One horizontal component, let's say if I'm throwing it at 10 meter per second, it has a horizontal component of 6 meter per second and a vertical component of 8 meter per second. Now, I mean, it sounds confusing, isn't it? How come 10 meter per second? Then this is 8 and 6. Now, actually, there is only one, you only need to look at one of it. Let's say if you are looking at the 10 meter per second, then you don't have this. You don't have this. Now, when you break this velocity into two components, then you have something like this. Then you don't have this anymore, right? So these two, they are equivalent. You see the equivalent sign there? The three horizontal line, it means equivalent. So these two, they are equivalent, but you can only look at it one at a time. You can only look at it as 10 meter per second at an angle with the horizontal, or you can look at it like this with a velocity of 8 vertically and with a velocity of 6 horizontally. Now, what does it mean? It means that, let's say if you have 1 ringgit, 1 ringgit. Now this 1 ringgit, you can convert it into two 50 cents, right? Or if you don't want to look at it as 2 50 cents, you can look at it as 1 ringgit. But how much do you have? You only have 1 ringgit. You can either convert it to one single dollar note or two 50-cent coin. You cannot have both at the same time. Okay or not? You see this thing here. the analogy
Yep,
here.
yep.
Okay, either you want to have 1 ringgit, right? 1 ringgit, you keep it as 1 ringgit, then you look at it, it's only 1 ringgit. Or you don't want the 1 ringgit, you go and change it. Okay, you change it for 2 50 cents coin. So I say that 1 ringgit is equivalent to 2 50 cents, right? Now the actual value that you have is not 2 ringgit. You only have 1 ringgit. So if you want to convert it to 1 ringgit, then it will be like this. If you don't want this 1 ringgit, you want to convert it to 2 50 cents coin, you only have 2 50 cents coin. So overall, the value that you have is only 1 ringgit. The value that you have is only 1 ringgit. You don't have 2 ringgit. You don't have 2 ringgit. You only look at the 1 ringgit as 2 50 cents coin, or you look at the 1 ringgit as a 1 ringgit note. Okay, so that is the analogy for this velocity at an angle there, right? So you can either look at it as a single velocity, or it is sometimes more convenient to look at it as two components. Okay, you resolve it into two components. That means you have this only. You no longer have this anymore, right? So you can only have one of it at a time, or you can look at it one version at a time. You don't go and overlap the two, and you think that you have two things, right? So you have only one, either this or this. Okay, now coming back to solving problem, right? So this velocity, right, we can resolve it into two components. The horizontal component, we call it v naught x, v naught x. But you must remember, as you throw the object, as the object leaves your hand, or maybe you imagine it as a shot put or a ball, as it leaves your hand, the velocity will change. Why the velocity will change? Because maybe you got air resistance, then it will get slower and slower, right? Or perhaps because even if you ignore the air resistance or the wind resistance, in most of these cases that we are going to solve later on, we assume that the air resistance and the wind resistance, they are negligible. Negligible means the value is very small and you can ignore the air resistance and the wind resistance. So assuming that there is no air resistance or wind resistance, then let's say we start off with a horizontal component of v naught x. We start off with a horizontal component of v naught x. Okay, that is this one, the horizontal velocity here, v naught x. And this v naught x will be the horizontal component. It is the same throughout the journey, throughout the flight. We don't call it journey, we call it the flight, no? Because the object is in the air, so we call it flight instead of the journey. Where is it? Yeah, okay. It is called the flight. Flight. It's called the flight, right? And the path taken is called the trajectory. Okay. So there are two words that they use here. If this path, this line, this parabola, the dotted line here, is called the trajectory of the parabola. Now, when the thing, when the projectile is in the air, we say it is in flight. It is flying, lah. So it's in flight. So the journey is called the flight. Okay, right. Now, we look at the horizontal component of the velocity, v naught x. And throughout the journey, at every stage here, at every stage during the flight, you see they have frozen the object along the trajectory. Let's say at this position, initial position, there's a certain horizontal component and a certain vertical component. So as you, let's say we take this position here, there's a certain horizontal component and a certain vertical component, and here and here and here. So along the trajectory during the flight, the at every stage there's a vertical component and a horizontal component of the velocity. However, the horizontal component of the velocity will not change. The horizontal component of the velocity, you see at this point here, there are two lighter color arrows. What color is this? Is it orange? The lighter color one?
Uh,
Is
so
it
so
orange?
I'm a colorblind. I'm colorblind. Cannot see colors.
Oh, this is red color. This is red color.
Okay, that one I
Then
can
this
see.
this
The
one
one
is
you asked, I don't know.
you don't know. This looks like orange to me, right? Now, at every stage, you can resolve the velocity into two components. Now, the horizontal component at each stage along the path or at each stage during the flight, it is the same. Because if there is no wind resistance, nothing will reduce the horizontal component of the velocity. Nothing will reduce it. So we say here that the Vx, which is the instantaneous velocity, horizontal component of the velocity, it remains the same throughout the flight. It remains the same throughout the flight, and it is V naught x all the time. The horizontal component is V naught x all the time. Okay, now since the velocity is constant all the time, we want to know what is the displacement, how far it has traveled. So the horizontal displacement is V naught x multiplied by the time. Now this distance here, this displacement or this distance here, is the horizontal distance covered. Is the horizontal distance covered, and you can look at it as the distance along the x-axis here, the distance along the x-axis. So this is it. Where is it? Okay, okay. So this is the horizontal distance covered and also known as the horizontal displacement. This is the horizontal velocity. Now, if you are going to look at the vertical component of the velocity, this is the horizontal component and this is the vertical component. And the initial vertical component is V naught y. Now, this component is subjected to gravitational pull. The horizontal component is not affected by anything other than air resistance, which we already say it is negligible. But whether you like it or not, the gravitational pull will affect the vertical component. And how the gravitational pull will affect this vertical component, so we look at it over here, right? We look at it over here. The vertical component of the velocity, Vy, Vy, Vy is the is the instantaneous vertical component of the velocity. Instantaneous means it can be the vertical component of the velocity at at any particular time, any particular time. So this one follows the equation of motion when it is subjected to a gravitational pull. So the initial velocity, the velocity, the final velocity at that particular instant is the initial velocity plus the acceleration times t. If you remember the formula, I left it somewhere here. I try to copy it into this page. Where is it? Where is it? This one. Okay. This one, I try to copy and paste it into this page. Okay. So I paste it here, right? Okay. So what we are looking at is the first equation. v equals to v naught plus at. But this v equal to v naught plus at, we are now applying the vertical component of the velocity into this equation. We are applying the vertical component of the velocity into this equation. So this equation say the final velocity is the initial velocity plus acceleration multiplied with time. So when this is translated into the vertical component of the velocity, so the instantaneous vertical component is the initial vertical component plus negative gt. The acceleration is negative g. So negative g times t. So here we have an equation for the vertical component of the velocity. Okay, next we are going to find the vertical displacement. So the vertical displacement, we don't call it delta x lah. We call it delta y because vertical. So this delta y, we are going to use the second equation. The second equation. The second equation says the change in displacement is the initial velocity multiplied by time plus half at squared. So applying this into our vertical component of the velocity, the vertical displacement, okay, at first this is the change in displacement. So we translate it as the vertical displacement, initial velocity times time. So is the initial horizontal vertical component times time, then plus half at squared. A is negative g. So using these four formulas, we are able to trace the velocity of the object. We are able to trace the position of the object on the xy plane. Okay, xy plane means how far in front you go, how high you go, right? Xy plane, right? So any questions regarding these four equations here?
No, sir. No, sir.
No. The first two
Mm,
represents the velocity and displacement horizontally of the flying
mm-hmm.
object, or we call it the projectile. The second two, the next two represents the velocity and displacement vertically of the object or of the projectile. Okay, no question. Okay, no question. Then